Hereby, I open this academic ceremony in which Moritz Buchem will defend the academic thesis, Biking in the Scheduling Landscape, Exact and Approximation Algorithms for Parallel Machines. May I invite you to present a summary of your study and the conclusions of your thesis.
Thank you, Prorector. Dear Prorector, dear members of the Defense Committee, dear colleagues, family and friends, thank you for joining me today. In the next 15 minutes, I will give you an overview of my thesis titled Hiking in the Scheduling Landscape, Exact and Approximation Algorithms for Parallel Machines. To start with, I would like to give you a summary of the main themes of my thesis. So a schedule is an efficient allocation of resources to activities over time, and finding such allocation plays a vital role in many fields like logistics, public transport, public education, and many others. So consider, for example, the following two examples of decision makers. On the one hand, we have a car rental company, and this car rental company has to clean its fleet of cars once a week, and there are some employees responsible for doing so. So the task of this car rental company is to find a schedule for cleaning these tasks as efficiently as possible, so to minimize the time at which the last car is cleaned. On the other hand, we have Santa Claus. Santa Claus has a different problems. He has to distribute gifts to kids, and he wants to make every kid as happy as possible, so he wants to maximize the happiness of the least happy kid. And as it turns out, these two seemingly unrelated problems can be modeled in one general framework by scheduling problems. In my thesis, I focus specifically on scheduling on parallel machines. So parallel machine models are scheduling models where we have a set of machines, and these machines can work or process jobs in parallel at the same time. However, each machine can only process one job at a time. Now, if we go back to the two examples from before, this would mean that for the car rental company, the machines would be employees, the jobs would be cars, and the objective would be cost minimization, for example. For Santa Claus, the machines would be children, the jobs would be gifts, and the objective would be happiness maximization. Now, once we know how to model these problems, the next step is how to solve these problems. And this is where algorithms come into play. An algorithm is more or less a mathematical or computational recipe to find a solution. So it takes as input some information about your problem and gives you as output a solution to your problem. Of course, the goal is to find an optimal solution, or the ultimate goal. One way to do this is by an algorithm called enumeration, which simply considers all possible algorithms and takes the best of these, considers all possible solutions and takes the best solution. So it always guarantees to find an optimal solution. However, it does so in an inefficient amount of time in practice and theory. So the ultimate goal is to develop exact efficient algorithms. An exact efficient algorithm also guarantees to find the optimal solution. However, it does so in an efficient amount of time. So the time it takes to find this optimal solution is efficient. This is not always possible in theory because there are some problems for which it is very unlikely that exact efficient algorithms exist. So we have to choose a different way for these problems. And one of these ways is to consider approximation algorithms. An approximation algorithm is also an efficient algorithm, so it finds a solution in an efficient amount of time, but it does not guarantee that this solution is optimal. But there's some guarantee that it's near optimal, and this near optimality has to be guaranteed in a theoretical way. So there has to be some theoretical proof behind how good your solution is that you find. Now, in my thesis, I study various problems in the field of parallel machine scheduling with the goal of finding approximation algorithms or, if possible, exact efficient algorithms for these problems. In the first part of my thesis, I focus on deterministic scheduling. So here, the decision maker has full access to all information. So for example, Santa Claus, of course, he knows the value of every gift. He knows how many gifts there are, so he's a deterministic scheduler. In the second chapter of my thesis, I consider a problem or a family of problems called load balancing. And in load balancing, the objective is to balance workload between employees or machines, or find a fair allocation of goods or bads to machines or people. And as it turns out, this is a difficult family of problems. So exact efficient algorithms are unlikely to exist, which is why we study approximation algorithms for these problems. Now, in our work, we present a family of approximation algorithms, namely additive approximation schemes, and this family of approximation algorithms gives a nice trade-off between the quality of a solution and the time it takes to find this solution. So we can get really close to the optimal solution. However, the closer we want to get, the more time it will take to find this solution. In the third chapter of my thesis, I consider a problem called scheduling with machine conflicts. And here we are not only given machines to process jobs, but also a server to pre-process and post-process jobs. And now the challenge is that not all machines can be served at the same time due to some spatial or technical conflicts. We study this problem both from a general point of view, where we show that it's computationally hard due to the nature of the machine conflicts and their impacts on the feasibility of schedules, and we show that in special cases, we can gain some structural insights based on these machine conflicts to find or to develop exact or approximation algorithms. In chapter 4, I move to a problem called just-in-time scheduling, and just-in-time scheduling is relevant in settings where jobs have due dates, and we want to make sure that every job is finished close to its due date. So we have a cost for earliness and lateness. And more specifically, we consider quadratic earliness and lateness costs. We consider a special case where all jobs take the same time and show that if all jobs have the same priority, then we develop an efficient exact algorithm. And for differing priorities, we show that an efficient exact algorithm exists if all jobs have the same due date. However, if these due dates differ, we introduce an approximation algorithm. Now, as I mentioned earlier, all problems so far in this first part of my thesis were in the realm of deterministic scheduling. So in the second part of my thesis, we move on to scheduling with uncertainty. And this means that now the decision maker has no full access to information in advance. So for example, the car rental company, opposed to Santa Claus, they don't have full information, so they don't really know how long it will take to clean each car, since it depends on multiple factors. But they might have some information about how long it might take, so they have a distribution over the time it takes, for example. And in the fifth chapter, I study a problem in the area of stochastic online scheduling. Stochastic online scheduling models two types of uncertainties. So first of all, the time it takes for a job to finish is uncertain, and secondly, jobs will arrive over time. So the decision maker has to make decisions on the fly. And these two types of uncertainties, they come with an additional challenge. Because now a solution is not only a schedule, but it is a policy which has to make decisions on the fly. So, for example, if you think about the car rental company, whenever a car arrives at the station, they have to make a decision on, okay, when will this car be cleaned and by which employee? In this chapter, we consider a special setting where we talk about uniform machines. This means that every machine is associated with a certain speed at which it can process jobs. And furthermore, we consider the special case that each machine is either fast or slow. And from a theoretical point of view, we develop stochastic online policies and prove their performance guarantee in theory. And we complement this with a computational analysis of these policies. And this computational analysis actually shows that in practice, these policies may perform much better than in theory. In the final chapter, I consider a problem in inland waterways. So inland waterways are a crucial part of our logistics network. However, they come with a certain bottleneck, namely locks. So locks are responsible for moving a ship or a vessel between river segments to overcome differences in water level. And in our chapter, we consider the point of view of vessel A here, and vessel A wants to cross these two river segments and minimize its fuel consumption. However, there's also vessel B, and vessel A only knows that vessel B is there, but it does not know how much time it will take vessel B to use the lock. So there's some uncertain waiting time at the lock for vessel A. And from a theoretical point of view, we again introduce different policies, so optimal and near optimal policies for this problem, and we complement this with an empirical study which shows that actually taking uncertainty into account in such settings is quite important for decision making, because if we would only solve the problem as if there's no uncertainty and then face this uncertainty at the lock, this could lead to long waiting times and therefore an increase in fuel consumption compared to taking into account uncertainty. Now, I would like to conclude my talk by saying that my thesis focuses on the theoretical study of scheduling problems with and without uncertainty faced by many decision makers like Santa Claus. And in particular, we focus on the development of exact and approximation algorithms for these problems, where again, an exact algorithm is the best we can do. However, there are situations where we cannot achieve this goal, so we have to go back to approximation algorithms for this. And now I would like to thank you for your attention and give the word back to the prorector.
Thank you for your presentation. The opposition will be opened by Professor Dr. Stan van Hoesel, who was the chair of the assessment committee, and Professor van Hoesel, whose expertise is on operations research at this university at the School of Business and Economics.
Thank you, Pro-Rector. Dear candidate, dear Moritz, let me start with telling you that I read the thesis with a lot of joy. It is well written, contains lots of results, and it was time well spent for me. I learned a lot of it. My role here is to ask a question, so that's what I'm going to do. This morning I started to read your propositions to start with. And what struck me first was particularly proposition 5, and maybe one of your partners may read it out for the audience right now.
Simplicity pays off.
Maybe you could do it a little bit louder.
Simplicity pays off.
Thank you. I like simplicity. Unfortunately, there's nothing simple about your thesis. The algorithm you're referring to, I guess, in this proposition is the one in chapter 6 that is in itself very simple but very difficult to analyze, especially when you want to compare it to the other algorithms that you're talking about, the exact algorithms. Anyway, that's not what my question is about. My question is about something which is also very difficult. In chapter 2, you're talking about 3 problems. The first one is very well known, minimizing the make span of a machine loading problem. So minimizing the maximum load. You also have the version where you maximize the minimum load. And then the Santa Claus version where you minimize the difference between the maximum load and the minimum load. And that problem turns out to be much more difficult to analyze than the first 2. So I wonder whether you can give me an answer to the following question. Let's consider a problem, find out what the minimum make span is, find out what the maximum minimum load is, consider the difference, and then solve the Santa Claus problem, minimizing the maximum minus the minimum. Can you give an example where this last problem has a larger value, objective value, than the difference of the 2 objective values of the first? And if so, can you also give me something about the ratio between the 2?
Dear highly esteemed opponent, dear Stan, so first of all, thank you for your kind words. So, of course, if you have an approximation algorithm for the minimum make span and the maximizing the minimum machine load, combining the 2 gives some approximation guarantee on the NV minimizing Santa Claus objective. For the case that the Santa Claus objective is much larger than the difference, I'm not sure of an example right now, but for example, if you have more than 3 machines, then already this middle machine can make this problem quite difficult, right? So for 2 machines, the problems are all equivalent, but if you have at least 3 machines, then this machine in the middle can be anywhere, so this makes the problem a bit more difficult than the other 2.
Yeah, thank you.
The opposition will be continued by Professor Dr. Sanita. She's online. She's also a member of the assessment committee, and she's a professor in computing science at Bocconi University. The floor goes to Professor Sanita.
Thank you very much. So, dear candidate,
First of all, I would also like to say that I enjoyed reading your thesis, and as it has been already said, it contains a very nice set of results. So I would like to ask the following questions. You have done a lot of works in developing FPTEs, repeaters, PTEs, and I would like to mention that very often PTEs, algorithmic results of this kind, translate, especially if based on dynamic programming, translate into polyhedral approximation. So this would translate into have an approximate relaxation for your problems with kind of arbitrary precisions. So I would like to ask if this is the case also for your problems, if you have thought about it, whether you can translate the algorithmic approximation that you have into polyhedral approximation, like it happens for knapsack.
Dear highly esteemed opponent, dear Laura, so first of all, thank you again for your kind words. If I understood correctly, you were asking if the approximation algorithms translate into polyhedral approximations of relaxations of the problem. So I'm not sure about polyhedral approximations, but in chapter 2, the idea of these algorithms is exactly that we find a solution to a relaxation of the problem and basically find an approximation to this relaxation.
Okay, that is a bit. Oh, okay, sorry, I hear a bit of echo. So, okay, it's a bit different. So it's not just having an algorithm that relates on an LP, like having a polyhedral approximation as it's more than that. But okay, like it's not a problem. I mean, it's not immediate that an algorithmic result of this type can be translated into a polyhedral approximation. There is some work to do, but as a suggestion, there are general techniques, especially if your approximation is based on dynamic programming, as in some of your cases, that's exactly what is happening, then that could lead to a stronger result. So maybe this is something to take into account. And yeah, if just one small other thing that I would like to ask that is related to chapter 3, in which you have machine conflicts. I wanted to ask, as far as I understand, there are 2 levels of difficulty that we are adding with respect to some of the peer work. So you are considering both pre and post processing, and you are considering conflict machines. I wanted to ask if like having just one of these difficulties makes the problem easier. For example, just having pre-processing and not post-processing, or if maybe this is actually not simplify the problem too much.
Dear highly esteemed opponent, dear Laura, thank you for this question as well. So there has been some work on these cases where we either have pre-processing or only post-processing, mostly pre-processing. And the problem can be a bit simpler this way because we don't have this nested cases of schedules anymore. Because so for example, if we only have pre-processing, we have a bit more freedom on the end of the job to combine it feasibly with other jobs. Still, there is some work that shows that for complete conflict graphs, this is still NP-hard, even if the pre-processing is identical over all jobs. But there have been some generalizations of list scheduling, and I assume this could be also generalized to more general conflict graphs. So if your conflict graph is not a complete graph, but for example, a bipartite graph, as we mainly consider, I could see that maybe if we only have pre-processing, maybe this makes things a bit simpler since we can have these nicer structures of schedules or of sub-schedules. Yes.
Okay, thank you.
The opposition will be continued by Professor Dr. Scutella. Professor Scutella was the 3rd member of the assessment committee. He's the Einstein Professor für Mathematik und Informatik at the Technische Universität Berlin. The floor goes to Professor Scutella.
Yeah, thank you very much, Prorector. Dear candidate, dear Moritz, so first of all, thank you very much for your very nice presentation that you gave at the beginning of this session of your thesis. It was a great pleasure for me to read your thesis, and I really like your results. I like the content of your thesis, and I can say I learned something while reading it, so thank you very much for that. Whenever I'm at the defense in the Netherlands, I always look forward to reading not only the thesis but also the propositions. So that's what I did as well. And I'm not sure whether I agree with all your propositions fully. And I would like to ask a question about proposition number 7. So maybe could you please write this for us, or ask your friend to write it to read it for us?
Ignoring uncertainty comes at a higher cost than what we can gain with even simple techniques which take uncertainty into account.
Yeah, thank you very much. So this is a good statement. As I said, I'm not sure whether I agree fully with this, so I would like to ask you the following. Let's say we talk about stochastic scheduling here, so that's also what you did in your thesis in some parts. And can you show me particular examples, stochastic scheduling problems where your statement, your proposition is provably true? And can you also show me a counterexample, some stochastic scheduling problem where your statement is provably false?
Dear highly esteemed opponent, dear Martin, thank you for your kind words and for the question. So for the first part of your question, I would say if you have a probability distribution of your processing times and these have large variances, then only taking the expected processing time in your scheduling decisions could lead to some large errors compared to taking into account in the analysis also the variations. So if you compare your stochastic scheduling solution to the deterministic scheduling solution, for your second part, for the counterexample, so if I understand it correctly, you mean that ignoring this uncertainty would be better, or at least as good as taking uncertainty into account.
Yeah, so what you said previously goes into a good direction. So you said I could, in some settings, maybe only consider the expected duration of jobs. Are you aware of simple stochastic scheduling problems where this information, just knowing the expected values, would be enough to find an optimum solution?
Yeah, so for example, if you want to minimize sum of weighted completion times on a single machine, there we use Smith's rule, which only uses the weights which are deterministic and the expected processing times, yes. So there, the additional information we could have from the distributions will not help, yes.
Yes, indeed. So thank you very much. That was one of the examples I was thinking of. On a single machine, we don't actually need this information. So how would the situation be if you go to two parallel machines, two identical parallel machines? You think that you need information on the distributions to come up with optimum schedules there?
On two parallel machines, it's still fine if we have some more information about the processing time. So if we have processing times that are with agreeable weights, so that Smith's rule also implies a non-decreasing order of the weights. However, if we go to more machines, I think, so for 3 machines, I think it's still fine up to 5 jobs. This is what I think people know, but for 6 jobs and more, we don't know if having these agreeable weights in addition to Smith's rule helps. So already there, some more information would be needed, yes.
Yeah, thank you very much for your answers. That's very good.
Thank you. The opposition will be continued by Professor Dr. Nicole Mego, who was also a member of the assessment committee and whose professorship is on combinatorial optimization and logistics at the Universiteit Bremen. The floor goes to Professor Mego.
Thank you. Dear candidate, dear Moritz, I also want to start with congratulating to your nice thesis. It was a pleasure to read it and to see your nice results. I would like to start with a question on your additive p-tests. So you show for several load balancing type problems that you can show additive approximation schemes. And my question is, there are other classical scheduling problems, for example, minimizing the sum of weighted completion times on several machines. There are multiplicative approximation schemes are known. And I was wondering whether your techniques or parts of your techniques might apply also for other objective functions, or if not, if you have thought about this, what kind of obstacles are there?
Yes, dear highly esteemed opponent, dear Nicole, thank you for your kind remarks. So one challenge with our approach already would be that in our approach we find a schedule where every machine load deviates by epsilon p max from the optimal load of this machine, or the load of this machine in an optimal solution. So even if you take, for example, the LP norm of the machine loads, you might come into issues because you have these epsilon p max errors over multiple or over m machines. And similarly for sum of weighted completion time, or I would see the issue that these epsilon p maxes, they start adding up, right? So you would have something like epsilon n times p max, and at some point you cannot bound your, so you would have an additive approximation algorithm with something like n times p max, but this is of course not an improvement over the classic multiplicative approximation schemes, whereas in our case there are cases where p max is much smaller than the optimal, or for example for the envy minimizing center clause where a multiplicative approximation scheme is not possible. So the main challenge with our approach is this summing up of these deviations from the optimal solution. So I think there maybe other approaches would work. We did not think about this in much detail yet, but there would be some extra work that these local deviations, so for example from the job completion times, would be much smaller than what we can show with our approach.
Yeah, I fully agree that this piling up, when one only looks at the make span or the summation of these processing times, this may not work. Let's say for sum of completion times, we typically structure the instance and then round job sizes to classes, or also structure the time axis. Is there any idea from your previous work for the make span where you would say, if I aim for an additive approximation scheme, if I could dream, then this type of technique or this idea I would try out first?
So I think rounding has the issue again of this piling up, because if we round to multiples of epsilon p max, in the end we have to unround the processing times again. So I think what would be a possible way is to do something similar like we do, that we don't round but somehow group these jobs in similar classes and can in the end round the solution rather than the input. But this is not clear how this would work for sum of weighted completion times, for example.
Remains an interesting question. And as a final add-on to this, did you compare in some way multiplicative and additive approximation schemes? How would you compare them? What would you quantify?
So, as I mentioned, for problems where no multiplicative approximation guarantee exists, that's easy. And for example, for the make span, what you could do is estimate the optimal and compare to Pmax in our case, the maximum processing time. And then, of course, if the maximum processing time is much smaller than the optimal solution, the additive approximation guarantee would lead to an improvement. However, I have to mention that the additive approximation guarantee that we obtain is a p-TAS, so an additive p-TAS, and for the multiplicative approximation guarantee, EP-TASes are known. So this would again be a comparison of both the approximation guarantee but also how fast we can find this solution.
Thank you very much.
Thank you. The opposition will be continued by Dr. André Berger. He's the last member of the assessment committee, and he's an associate professor in operations research at this university at the School of Business and Economics. The floor goes to Dr. Berger.
Yeah, dear candidate, dear Moritz, first of all, congratulations on a very well-written thesis. I really enjoyed reading it. It contains many different results in machine scheduling. And I have a question about chapter 4, just-in-time scheduling with quadratic penalties. So in this problem, there are due dates for the different jobs that have to be processed on the machines. And typically a due date is something where the job should be finished, right? But in this case, the penalties are the same independently of whether you're done before or after the deadline. And yeah, that can be the case in just-in-time scheduling. And I'm wondering if you also think these results can be obtained for similar objective functions that are maybe not quadratic around the due date, or maybe not even symmetric, right? So my more detailed question would be whether the first two observations that you need, observation 4.1 and 4.2, would also hold in if the penalties are not symmetric around the due date, because you make quite some use of these.
Dear esteemed opponent.
Maybe, you can go ahead.
Dear esteemed opponent, dear Andre, first of all, thank you for your kind remarks. So observation 4.1, if I'm correct, is about these V, or this inverse V shape of a schedule.
No, that comes later.
Ah.
So observation 4.1 is about the completion time and the due dates of the jobs.
So that a job with an earlier due date will also finish at an earlier time. I think, so if we consider, for example, still squared deviation and non-symmetric weights, so that earlier could be more expensive than later, then I guess this should still hold for jobs with different due dates, because we could still make the swapping argument. However, we might not have this symmetric schedule around the due date anymore, right? Because it could be that, so for a single due date, it's better to be a bit late with some jobs than to be early, so we don't have this symmetric schedule around this due date for a single due date anymore.
Okay. And then I wonder, your results are about some special cases, right? Unit weights, or just one machine, or just one due date. So it seems to be a rather difficult problem, because for all the other scheduling problems, we can solve much more general problems. So can you say a bit about why you think, or what the characteristics of this problem are that make it so difficult, or where would be the first point to tackle a more general problem?
Yeah, so I think the main challenge is the quadratic penalties. So if we consider this problem with linear penalties, so the absolute value, it actually turns out that for a constant number of different due dates, which we consider in the final section of this thesis, this would be just an assignment problem, because we have a linear number of possible starting times for the jobs and a linear number of jobs. However, in our case with these quadratic penalties, the starting times are not at integer point in times or at a linear number of times. So this is one main challenge to obtain something better for a general setting. And then to go away from these unit time jobs, this is even more of a challenge, because you also have to consider more closely even the order of the jobs, because you don't even have only have the weights of the jobs, but also the processing times, which then again determine the completion times of the jobs, whereas we can just say, okay, if we know a job starts after this job, it will be a certain amount of fixed time units after this one, or a constant amount.
Okay, thank you very much.
Thank you. The opposition will be continued by Dr. Marjan van den Akker. Dr. van den Akker is Associate Professor in Operations Research and Artificial Intelligence at Utrecht University. The floor goes to Dr. van den Akker.
Thank you. Dear candidates, dear Moritz, In the first place, congratulations with this great results that you obtained in your thesis. It was a great pleasure also for me to read in it. I want to talk a bit with you on chapter 6 on the logs. So there is a vessel A which wants to optimize its speed given that the behavior of vessel B is uncertain, and that uncertain behavior is in the docking and undocking time. And you state that this time follows a truncated geometric distribution. Can you elaborate a bit on why you assume this?
Dear esteemed opponent, dear Marianne, thank you for your kind remarks. So this truncated geometric distribution we actually got from real-life data of log processing times, and this is, so of course, log will finish at some point, so this is where the truncatedness comes from, so it will not go infinitely. And you could intuitively think of this as the vessel and the log operator having trials to finish processing the log, and then whenever this fails, there's an additional unit of time. So this truncated geometric distribution was what we saw nicely matches this real-life data.
Okay, thank you. Because still it's about a time, which in itself is a continuous entity. So if I would suppose that there would be a continuous probability distribution, what would be the consequence for your algorithms, for your approach? Would it still work, or would it be extremely difficult? Or
so the challenge would then be that the velocity policy would of course also need to make continuous decisions, because we now show that in this case of having a discrete distribution of the log processing time, the decisions we make are also at discrete points in time, and only when we receive additional information about the state of the log. So in the case of continuous distributions, we would have to look at continuous velocity policies.
And would that be doable, do you think, or would it be?
I would think that
just it's speculation at this point in time, of course, but...
So even now in our discrete case, we already had to make more discretization of the decisions the velocity policy can make, because of course you can also think of the river segments to be continuous. So there we made even more discretization. So I would say if we also have the case of continuous distributions, there would be quite a challenge to find velocity policies without making additional discretization somewhere else.
Okay. Thank you.
Thank you. The opposition will be continued by Professor Dr. Dries Vermeulen, who is not present, but his question will be later on posed by Professor Van Hoessel. The floor goes now to Dr. Rohwedder, who is present. He's an assistant professor in operations research at this university, the School of Business and Economics. The floor goes to Dr. Rohwedder.
Dear candidate, dear Moritz, I was very impressed by the combination of both conceptual and technical ideas in your thesis. My first question is about the additive Peters in section 2. So according to a definition in your introduction, this Peters is not efficient. So could you please broadly discuss whether you consider this algorithm efficient, both from a theoretical and from a practical perspective?
Dear esteemed opponent, dear Lars, thank you for your kind words and for your question. So an efficient Peters would have the dependency of 1 over epsilon outside of the exponent of the size of the input in the running time. So I think here, since we, for the first solution method, have a double exponential running time in 1 over epsilon, I think even if we want to get something closer than half Pmax or a quarter Pmax, this would explode quite quickly in running time in practice. So of course in theory this would still be polynomial, which some people see as efficient, but in practice having a polynomial of n to the power 10 or 12 would already be quite inefficient. And to compare this to, as I mentioned earlier, to the multiplicative approximation schemes, this is where the efficient p-tasses already exist. So this is one next step for future research one could consider to improve these additive p-tasses to efficient additive p-tasses. But there we can see that most of the techniques used for multiplicative approximation schemes fail.
Okay, I understand the direction of improving the theoretical guarantee to an efficient p-tass. You also mentioned that in practice this kind of running time is probably intractable. Now, could you still take some of the ideas from your algorithm and maybe use them in a more practical way? Could you imagine some approach how to transfer some of these ideas to practice?
So I could think, for example, the local search we use in this algorithm already has a relatively large exponent in the running time, but I guess that this with some good initial solution, which will then not be optimal, but it will give also some fractional solution to the relaxation, this could work. So if we just start with any arbitrary solution, which will then also be a feasible solution to the relaxation, we can get close to this solution. So this is actually the one nice part about this local search, is that it does not depend on the solution to be optimal, because for any solution it will give you, or for any fractional solution, it will give you some guarantee on the rounded solution.
So that is the second part of your algorithm. So the first part is solving an MILP relaxation, and I agree that this local search algorithm itself appears much more practical. So your approach to solve the MILP solution is based on some sparsity argument about the solution. Now, sparsity also plays a role in practical ILP algorithms, for example, in column generation. Does that, do you think this could be a way to potentially make this part also more practical?
Yes, so I think that maybe the first approach we have to solve the slot MLP, where we just guess all possible solutions, if we have some smarter way like column generation to find or give us the better guesses of this, or give us better guesses of these this optimal solution or this optimal slot vector, then I think this would also lead to more practicality, or could lead to more practicality of these algorithms. Yes.
Okay, thank you very much.
Thank you. As I mentioned already, Professor Dries Vermeulen regretfully is ill, but he met with Professor van Hussel, who picked up his question. So Professor van Hussel will now pose the question of Professor Vermeulen.
Okay, sorry for being ill, is what Dries said, but he asked me to pose his question. He's a game theorist, so you get a game theoretical question. The point is, how do you get a game theoretical question from which chapter that would be, I would say, because in games you have 2 or more players, and the only thing that looks like a game here has only 1 player. That's the problem that you pose in chapter 6. Where there's 2 ships, and 1 ship faces a decision problem given uncertainty on the arrival of the second ship in the, part where he is shut down to a lower level. Now, the extension to a 2-player game should be very easy. Let's consider that ship B is in the same position as ship A. Namely that he faces the, uncertain arrival time of ship A at the barrier, whatever it's called, forgot the name. So, both face the same situation and have to find the optimal solution. You see how that can, work out. Ship A thinks, okay, I want to be just before ship B arrives, and pushes a little bit with speed, and ship B then sees that ship A is pushing a little bit, so he's pushing a little bit as well, and they go faster and faster to end up at their maximum speed, arriving at the same time. So that's the game that we're going to play. It's probably not as simple as it is not as simple as the problem that you discussed, but hopefully you gave it some thought, and that would immediately raise one or two questions, namely, is there an equilibrium for this game, or is there an optimal algorithm for this game? Are there more equilibria, or whatever? Could you elaborate a little bit on this problem?
The highly esteemed opponent, dear Dries or Stan. So this game theoretical approach to this problem has actually also been considered in other work, and there they show that from an equilibria point of view, a Nash equilibria is not guaranteed to exist. So there are instances where basically what you said, the speed up, where one ship can also always deviate from its current strategy to improve, and then the other ship will deviate as well. And what is done in this work is to introduce some pricing scheme to the ships, or to the skippers in this case, where they pay a bit extra, or where you charge them something or give them a monetary value to ensure this existence of a Nash equilibrium. And if I'm correct, this also works for more than 2 players.
Yeah.
Now, if you would, instead of considering an equilibrium, consider something like social welfare, so the objective of minimizing the fuel consumption of both vessels, this would already make it very complicated for 2 vessels, because even if in this setting we consider that the log processing time of vessel A is uncertain as well, and we only want to minimize the fuel consumption of vessel A, this would include finding the roots of a polynomial of degree even larger than 6, or at least 6, and this is already quite troublesome. So if then we also have to make decisions for vessel B, and both of them face uncertainty, I could see that this problem becomes very difficult if we blow up the number of ships.
I see. Thank you very much.
Thank you. This means that we've concluded the first round, and doesn't mean that the defense is finished. On the contrary, we'll follow up with a second round, and it's a custom at this university that then the floor goes to those who are furthest away, and that's Professor Sanita at the Bocconi University. So I'm happy to give the floor once again to Professor Sanita. The floor goes to her. Although we're looking at Professor Scutella.
Now, okay, can you hear me? Yes, okay, good. Thank you very much for the floor again. I have a very quick question, and this times it would be for chapter 4, and in particular for 4.3, where it is a single common due date and general weights. At a certain point, you do a distinction between restricted and unrestricted case. And you state for the restricted problems, finding an optimal assignment of job machines is a bit more challenging. Can you make this a formal statement? So is it formally hard, or do you expect this to be the case?
The highly esteemed opponent, dear Laura, thank you for this question as well. So actually, in our continuation of this work, we found an improvement of this, that that solving this problem is not exponential in the number of machines anymore, but polynomial. And this is by a smarter argument of this early and late machines, that we first don't have to guess if a machine is early or late, but that we can just sort the machines by early or late, similarly as we do in the algorithm right now for the early and late machines separately. So this problem can be solved in polynomial time for a constant number of machines.
I see. Very nice to hear that.
Thank you. I will then give the floor to Professor Scutella, who was already shortly present, but now he can definitely get the floor. Professor Scutella.
Yeah, thank you very much, Prorector. My second question is, again, on one of your propositions, and that's proposition number 6. And I doubt that proposition number 6 is true. I'm quite sure that it's not correct, while I understand what you mean with the proposition for most natural combinatorial optimization problems. this should hold what you write, but I think it doesn't hold in general. So maybe your friend can read the proposition and you have a minute to think about why that could be false, what is written there.
A strongly NP-hard optimization problem does not admit a fully polynomial time additive approximation scheme unless P equals NP.
Yes, dear highly esteemed opponent, dear Martin. So here, similarly to multiplicative approximation schemes, if we would have a fully polynomial time additive approximation scheme for a strongly NP-hard problem, then if the instance-specific parameter that we choose in this fully polynomial time additive approximation scheme can be bounded by a polynomial of the input size, then we could simply set epsilon to 1 over this polynomial or 1 over our parameter, and this should give us a pseudo-polynomial time algorithm, which should not be possible unless P is NP.
Right, so you already made one restriction here, right? So you said, if I can restrict the objective function value in a certain way. So do there exist problems where this, your assumption, your natural assumption that you mentioned, where this does not hold?
I mean, one very artificial problem would maybe be a scheduling problem where the individual processing times are exponential in the number of jobs you have. This could be a setting.
Yeah. Something in this direction, and what you say is true. I mean, you need to come up with an artificial problem. For natural problems, what you say is almost always true. Yeah, so that's a good answer. Thank you very much.
Thank you. The opposition will be continued by Professor Mego, if she wants to. The floor goes to Professor Mego.
Of course I want to, thank you. Dear candidate, dear Moritz, I have another question on chapter 5, and we didn't talk so much about this chapter yet. It's about stochastic online scheduling on uniformly related machines. And you consider there are 2 different types of online models, online list model and online time model. Maybe in a second you can remind us what this means. What my question is about the type of algorithm you use. You use a greedy type strategy, a min-increase policy, and in the online list model, you take a deterministic assignment of jobs to machines, whereas in the online time model, you use a similar strategy, but the assignment of jobs to machines is then in a randomized fashion. And my question is why? Randomized and not deterministic. But maybe you can start with reminding us of the model.
Yes, so dear highly esteemed opponent, dear Nicole, the difference between the 2 models is that in the online list model, all jobs are still available at time 0, but they are presented to the scheduler in a list. So the scheduler does not have access to all jobs at the same time. And in the online time model, jobs are presented to the scheduler whenever they are released. So the release dates might be non-zero. And the idea in the online list model is indeed that we have this greedy fixed assignment, and this nicely generalizes what is known in the identical machine case. However, in the online time model, there we saw that if we choose this greedy fixed assignment, bounding the completion or the expected completion time of a job or the weighted expected completion time of a job is not as easy as in the case of the online list model. So there we had to use a result that's known for unrelated machines about the expected completion time of a job for unrelated machines, which of course also works then for uniform machines. And then with this upper bound on the expected completion time or the conditional expected completion time of a job if it is assigned to a specific machine, and the random assignment of the jobs to machines based on the machine speeds then also leads to a nice bound, whereas just a fixed deterministic assignment, at least not the generalization of the one used in the online list model, does not lead to such a bound.
Mm-hmm. Thank you.
Thank you. The opposition may be continued by Dr. Berger, if he wants to.
Thank you. Dear candidate, I'd like to follow up on my previous question. We talked about the objectives for just-in-time scheduling, and you said that linear objectives around the due date would be easier to handle. So my question would be, what is the motivation to consider quadratic penalties in this case? And would they, let's say, ever come up in the examples or applications that you have in mind?
Dear esteemed opponent, dear Andre, thank you for this question. So the motivation behind quadratic penalties was actually coming from this application of vessel velocity optimization on inland waterways, because there you can see that if we only have a single vessel and we have a single lock and two waterways, we can compute the optimal time for this vessel to arrive at the lock, if the lockage time of this vessel is optimal. And now if we would have multiple vessels, of course we cannot put all vessels into the lock at the same time. So the deviation from this optimal arrival time at the lock will lead to an increase in fuel consumption, and this fuel consumption is usually quadratic in relation to the speed of the vessel, and then the speed of the vessel or the velocity is influenced by the arrival time. So an earlier arrival would lead to a quadratic increase in fuel consumption on the upstream part of the lock, so before arriving at the lock, and then later arrival would need to lead to less time to cross the downstream segment after the lock, and this would also lead to a quadratic cost of fuel consumption. And in general, for example, as I showed on the slides, if you have some products which turn bad after a while, but they don't turn bad if it's a minute or so, but the longer it takes, the higher the degree of turning bad, or some storage costs, which then again are energy consumption and could be modeled in a quadratic fashion.
Okay, thank you very much.
Thank you. Dr. van den Akker will continue the opposition.
Yeah, dear candidate, dear Moritz, I'd like to continue with a bit more general discussion. So you work a lot on approximation, algorithms, and discuss performance guarantees like multiplicative ones and additive ones. So if I work for a bus company and I design a schedule and I tell them, well, this schedule is great, it's at most 5 times the optimal value, they will not be too happy. So I would like to discuss with you a bit how could performance guarantees, approximation algorithms with performance guarantees make it to practice. What type of guarantee would you prefer, additive or multiplicative, and what do you consider as reasonable values, and are they around?
Dear esteemed opponent, dear Marianne, thank you for this question. So of course reasonable values are quite subjective. You could think for cost minimization, if you have to pay twice as much as you would pay in an optimal way, maybe it's worth spending this extra time to find the optimal solution, right? Or 5 times as much. And what you could see maybe for additive approximation algorithms, it's that the optimal value is not known to the decision maker, but this additive instance parameter is known to the decision maker, right? So for example, the maximum processing time is known to the decision maker, so it would not be 5 times the cost of the optimal solution, which is rather vague and not very tangible, but it would be the optimal solution plus whatever your largest job is.
You still may conclude your response.
Okay, so the largest job for the bus company could be, for example, the largest trip, which they do know. So there might be some practical advantage there. Yes.
Thank you. Moritz Buchem, the time appointed for defending your thesis has passed. and the degree committee will now withdraw to discuss the quality of your thesis and the quality of your defense. And I request that you and your company await the results of our deliberations and our return in this room.
Please all rise.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Long road to the south side. 10 miles in my rearview mirror, I know what it felt like. My goals only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. On the line, I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goals only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. The mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. And even though these nights seem long, I know that I am never on my own. Know you've won the battle once you've grown. South side, 10 miles in my rearview mirror, I know what it felt like. My goals only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goals only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile.
found your Lord and Savior Jesus Christ. Would you like to talk about stochastic optimization of scheduling?
I loved the first schedule, and then I stopped.
Moritz Buchem. The degree committee here present has assessed the quality of your thesis and the quality of your defense, and in view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Vredeveld is authorized to confer upon you this academic distinction in accordance with Dutch university custom, and I invite your supervisor to now take the floor.
Please all rise.
Is it on? Yeah. Do you promise to work in accordance with the principles of scientific integrity at all times? To be careful and honest, transparent, independent and responsible?
Yes, I promise.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Moritz Yannik Buchem, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present you with the degree certificate signed by the rector, the secretary and the other members of the committee and affixed with the official seal of the university. Dear Dr. Buchem, finally, dear Moritz, do you have a minute? And don't be afraid, my minute will not take as long as yours, because the product will not allow me to. So, do you have a minute? That is how, when this Dr. Buchem was still called Moritz, entered my office every time since you've been a research assistant in your second year of a master. A minute that normally took more than 2 hours, I think. And at a certain point I've learned to say, if I only had half an hour, no, I don't have a minute. But that took me quite some time to realize. So looking at the topic of your thesis, you're actually just a 150 multiplicative approximation, or we could say an additive 149 approximation, with high probability, by the way. So, dear Dr. Buchem, 9 years of Maastricht, and actually we've known each other for 8 years of those 9 years, as we first met during my second year course. 8 years, that's a long time, although actually in your duration of a minute it's less than 1 month. So, you spent your bachelor here. I taught you in this bachelor course, and then the next year you contacted me for writing your bachelor thesis. We had quite some fun in doing that. You wrote a nice thesis, and then you decided to continue with a research master. And, well, I was in close contact with you on shaping your curriculum, because the research master here in Maastricht has many advantages, and one of them is that you have a big choice of courses that you can take. And one thing that I still remember is that there was one course, somehow it did not fit, the schedule of the LLB program did not fit your schedule for graduating. And there was one course on Markov decision processes that you wanted to take, but nowhere you could really take it. So we decided, Maastricht University, innovative in learning, to set up our own Capita selector on this topic. And I also wanted to learn a little bit about it, so we gathered some more research master students, and we changed the roles. You were the teachers, I was the student, except for that I was grading by how much I learned. And the good thing was I learned a lot. So after a research master, then quite many students continue in a PhD. And I must say that by this time, having also supervised your research master thesis, your choice in supervisor became a bit monotonous. But I'm not complaining. So I was actually very happy that you stayed with us. We gave you in the first year quite some opportunities to discover your direction. You also had a lot of talks with Christoph, but in the end you went more into the approximation algorithm, so you stayed with me. I'm standing here, so I'm happy with that choice. It was a pleasure to see you grow. There was a steep learning curve during your during all your studies, but certainly also during your PhD time. And I still remember when we organized MAPS in Renesse. So we were the main organizers, so we did not have too much time during the day. So at a certain time, we were trying to work together with José Verchai. In the end, we got a paper out of it without José Verchai on the name of authors, but with Lars. So we were sitting with the three of us in a room. That's a good thing about being the organizer. You can just get the keys. And we spent some hours together in the evening. Things that we also did later, but then quite often more involved with some wines. So we finished that evening with several ideas that needed to be worked out. And I thought, okay, this is something he can spend some time on. The next morning at breakfast, do you have a minute? I'm not sure what I answered back then. I said I did not have a minute, but we still took some. It was a great pleasure to see this learning. And I think also Renesse was a good opportunity for your connection, for your network. I think there was the start laid for your later research that you did with Daniel. So that was summer of 2019. Half a year later, January 2020, when the university here was a bit offline, we went to Chile, to Santiago de Chile, to a workshop. And there we continued this research line, and it was also our initiation to start to cooperate with Lars and with Andy. And given that Lars is now with us, and you are now with Andy, I think it was a very good cooperation. So, after this trip to Chile, the lockdown came. And in the beginning, actually, this seemed to work well for you. Well, also at the end, it seemed to work well for you. You were very productive. You finished several papers, you started your collaboration with Daniel, and in the end, that led to a research visit to Berlin after lockdown, kind of in halfway. And all in all, it resulted in 5 research chapters, 4 published papers, and 1 that we hope to submit in the next year. So 5 research papers, whereas a normal thesis actually only needs 3. So that's quite some additional work. So it was already commented that you had a rather big thesis, which is true, but also nice. So at this point, I actually also want to thank the members of the committee for evaluating, because we value very much to have the opinion of national and international experts. And I also, of course, want to thank Tim for being your co-promoter. So, next to all this work, you still had time to be a bit social. Although I'm not sure whether I should call the PhD committee social. It has some official stuff where you can discuss with the faculty on the well-being of PhD students, but you also organize some nice social stuff. And I like that the tradition of the PhD students having lunch together with some additional staff when they were around has come back during your time, because that's something that I value very much, and it's also very nice for the social atmosphere. You also were every day when you were in the office organize some coffee breaks for the PhD students in the morning. Actually, for you, it was the start of the day, I recently learned, but that also helped to get the thinking process going. And I think you had a great deal in making new PhD students feel welcome here at Maastricht University. So, dear Dr. Buchem, dear Moritz, now the time has come for a parent to let his child fly out of the nest. It was a great pleasure to work with you. It was an even greater pleasure to see you grow. I had a lot of support from you when we had to discuss all the teaching and also all the research. Know that my door will always stay open for you whenever you want to have just another minute, even if it takes 2 hours. You're more than welcome to drop by, and I hope we can work together much more often. Let me finish by congratulating you and also to congratulate your parents and your brother for this very wonderful achievement. Congratulations.
Dear Dr. Buchem, also on behalf of Maastricht University, I congratulate you, your family and friends, and your supervisors, of course, with the degree you have acquired. I would like to thank the members of the degree committee for their contribution, and I would like to give the 2 members of the degree committee who are still online a short opportunity to congratulate you because that's for them a unique opportunity because they enjoyed your defense tremendously. In the meantime, I would like to inform all the others that it might be best after I close this that you go for the reception because we will have some pictures being taken here and then on the stairs, etc. So go for a drink. We will join you later and then each will be together. So the floor goes to Professor Sanita and Professor Scutella in this order. Professor Sanita.
Okay, so yeah, congratulations, Moritz. That was very, very good achievement. Congratulations to you, to your family, to your friends. And yeah, I already said it was very good reading your thesis. So, and I wish all the best for you and for your future. Many, many congratulations.
Thank you.
Professor Scutella.
Yes, also from my side, congratulations to you, to your family, your friends, and also to Jacques and Tim for supervising this wonderful thesis. Please remind me when we see each other next time that I owe you a beer for asking nasty questions. But then again, these questions were not nasty enough for you, as we could all see. So congratulations again.
Thank you.
Thank you. I will close this session and once again, please go and have a drink. We will join you later and we will go for the pictures. Thank you. I'll close this session.